Assalamu alaikum. Today we start the chapter number 6 of electronic devices by Floyd. The first point is amplifier operation. Let's start it. In last chapter we discussed about DC quantities. Now we use the AC quantities in this chapter. As AC quantities, already we mentioned you is a symbolic representation like this. The subscript is in small letter or shown this way, while instantaneously we use in this form, also in this form. This is the voltage and time graph of an AC signal. When signal reaches to the peak position where VCC is reaches at that point, while the average value of this of VCE is this, and RMS value of VCE is represented in that form. While what the next representation, the linear amplifier. There we discuss what happen when we give AC signal to the amplifier. This is our potential voltage divider. This is our voltage divider, and we give the signal at point A. If we read the voltage divider carefully, we say that this point is A in voltage divider, while when we give the signal to the point A by using this capacitor, we get the output across the load resistance RL at that point, while C1 and C2 is the coupling capacitor which used to block the DC voltage, while we give the signal at point A and we get the output signal at point this. ICQ is the amplified output signal, while VCEQ is the 180 phase of output signal. We get the output signal at ICQ because there is no change in the signal while amplify it and perfectly amplify it. So we always get the output signal at ICQ, not VCEQ. So our output is always at this point. We get the not at these 2 points, not get the output at these 2 collector and emitter points. I erase it. So the basic difference between this waveform and this waveform is that when current increases, the voltage decreases. When current increases to the maximum value, the output voltage decreases to the minimum value, and when current is decreases, the voltage increases. So there is 180 phase. across a collector current. Next, the graphical picture. This is AC load line. There is a difference between AC load line and DC load line. It we discuss it in the next chapter. There it mentions us only when AC load line IB increases or decreases, or when the current or signal give to the IB, like at that point when we give the signal at this point, that is IBQ, input voltage, input current, input current. Then IC is increase as this load line show that, and VCE is also increase and decrease but 180 phase. So Q point tells us what happen on load line of amplifier when the IB increase and then decrease. There it tells us. We discuss it in next chapter. This is an example. Okay, transistor AC models. First, it discuss about R parameter. This is these both values are we can calculate it IC, and which is equal to these values. These are the R parameters. So we remember all these R parameter: alpha AC, beta AC. Last time we discussed beta DC. Now we discuss beta AC, RE, AC emitter resistance, RB, AC base resistance, and RC, AC collector resistance. It also mentioned everything there. Okay, next, determined by RE, the emitter value. AC emitter resistance RE. Now we calculate it. What happened? This is the we make an internal circuit of transistor. Their base, emitter, and collector. RB base resistance, RE emitter resistance, RC collector resistance. As RC is very high as compared to RB and RE, so we use as an open circuit, and RB is very small, so we can remove it and make the circuit in this form. In this diagram, it the crystal type or diamond shape a circuit is basically depend upon beta AC IB or alpha AC IE. So it can be removed when base and emitter is forward bias. Next is what is the difference or comparison between beta AC and beta DC. This is the beta DC. Beta DC is basically equal to IC or IB. Why? Because the IC and IB is non-linear. There is a very small or slightly difference between beta AC and beta DC. This is the variation of 2 point like del IAC, del IB, del IC, del IB. This is also non-linear. While we get on beta DC the value at any point. On the other hand, we get the value of beta AC by using 2 points or more than H parameter. We also discuss these parameters in next chapters or remaining chapters. There we know what is HI, HR, HF or HO. HI, I for input, O for output, R for feedback ratio, F for forward current gain. When we use these amplifiers, common emitter, common base, common collector, the symbol can be changed by adding E, B and C. The relation between H parameter and R parameter. Alpha AC is equal to FB. Beta AC is equal to FE. And so on. These are also conversion of R parameter into H parameter. Now we start common emitter amplifier. I am going to the circuit. Again, the circuit is same, just we add one more capacitor C2 here. There C1 and C3 is a coupling capacitor and C2 is a bypass capacitor. When we give the input signal, we get the output signal in voltage form. This. In this diagram, he mentioned everything in calculation as C1 and C3 is 1 microfarad. On the other hand, R1, R2 is 22 kilo ohm and 6.8 kilo ohm, while RE, the emitter resistance, is only 560 ohm, and RC, the collector resistance, is 1 kilo ohm. We get the output. What we get? 6.2 at this point DC voltage, while beta DC is 150 and beta AC is 160 due to slightly difference. Everything mentioned in these topics. This is 180 phase. I everything tell you in last chapters or lectures. Next is the phase inversion. I also mentioned you DC analysis. We cut off all these AC or diagrams and only use the voltage divider like this circuit and calculate the values. RTH, we use the formula. VTH we also use, tells you everything about these things, and we calculate the values. IE, this is equal symbol, IE is equal to 3.58 milliampere. We calculate the meter current, then meter current nearly equal to collector currents, while voltage at meter is equal to 2 volt, base is 2.7, collector is 8.48, and voltage at collector and meter is 6.42. Now we discuss the analysis of AC. Their C1, C2 and C3 use as repulsion of DC, but no effects on AC signal or AC frequency. We drop all these AC connection to the base and use as act or they act as a base. We know that collector and base are connected to the VCC. There it mentioned it, connected to the VCC. So we remove VCC and act as a base or grounded. Act as a grounded. We ground the DC source. All the sources replaced by the ground signals. So this is the circuit diagram. Without input signal voltage, when we provide the input signal, then what happen? First, we replace it. These three resistance and by using R total, by using one resistance, because these resistance, base and emitter resistance also, which is represented here, is R in base, like that. We replace it and combine by using only one resistance, which is the total resistance at base. This one, R in total is equal to R1 parallel to R2 parallel to R in base. We use RS is very small. If we use the high RS, then VS signal, input signal, is decreases, which is disturb the Q point. Because if we go back, let's discuss in this example. We go back. As the input signal is smaller, the these point is also smaller, like in this form. Then the Q point is not stable, so we do not use the high value of RS. Now we go back to the our point. There it mentioned. So this is, we replace last these three resistance and by using equivalent resistance R in total, and base voltage is nearly equal to the source voltage. They mention you next, I think so. Yes, there is it. If R is very small to the R in total, then VB is equal to VS. Now we remove the now we use the circuit of R parameters by calculating R resistance in base, which is equal to V in divided by I in. V in is basically VB and I in is IB. R in base is that point. So VB, we know that VB is equal to IE RE. IE may be equal to or nearly equal to IC, while IB is equal to IE over beta IC. If we put these two things in this equation, we get this. By cancellation, we get the formula R in base, or we get the resistance on R in base beta AC RE. So the output resistance of common meter amplifier is R output is equal to RC, and R output is RC parallel to RC prime. Thank you.